there, this is video 516, where we're starting to talk about normal distributions. So this is the introduction, part 1. And you know a chapter on statistics has to, at some point, use the Guinness World Book of Records. Because you know what, I was just desperate to find some data. And it's not cool for me to make up all the statistics I use. So, here we go. According to the Guinness World Book of Records, the smallest cat ever was 19 centimeters long. 19 centimeters is, okay, so that's less than the page. Okay, and that was from the tip of his nose to the tip of his tail. And the longest cat on record is 120 centimeters, which is over 3 feet long, if that helps you. The average cat is 76 centimeters long from the tip of their nose to the tip of the tails. Now, here's where statistics comes in. Do you think there's a lot of cats that when full grown, when full grown, are only 19 centimeters long? Yeah, not a whole lot. That's pretty special. How about over 3 feet from nose to tail? No, not going to be a lot of those. I think most of the latest award-winning cats are Maine Coon cats. And I will just say, I grew up as a kid, and I didn't even know there were different breeds of cats. There was kind of like farm cats, and there was inside cats. Didn't actually know there were breeds. But anyway, most of the cats in the world are going to be somewhere around 76 centimeters, which is 2 feet, 2.5 feet, if that helps. If we were to graph enough cats, so if we went out and measured all the cats in Regina, from the tip of their noses to the tip of their tails, you would start to get a graph that looks something like this. Okay, now, important things. Where would the 76 be? Well, when you get a graph like this, the middle is always your mean. Okay, now the smallest one would be down here, which would be at 19 centimeters, and the biggest one, 120 centimeters. Okay, probably should have taken the numbers off there because they didn't help us much. So what this says is if you were to draw, okay, we're going to go backwards. If we think of this as a frequency polygon, you could imagine that it would help if I made them nice and even, that it was made up of a whole bunch of bars and histograms. And like in this one, there's maybe 1 cat and 2 cats and 4 cats, and it gets bigger and bigger. And then it would do the same thing, getting smaller that way. It doesn't matter what you look at. If you measure enough of them, most things will end up looking like this. Most things will have something at the low end and something at the high end. And those two things are pretty rare. And there's going to be like a big lump in the middle. So for example, if you look at the height in inches of US adult males, you have a few of them that are around 62.6 inches, which is like 5'2". And you have a whole bunch that are up here, most of them are around 70 inches. If you divide that by 12, that's like about 5'10". And you have some that are really tall. But most of them are in that middle part. And I love this picture. It's as good as I could get. But if you look carefully, it's a bunch of people. And those are 60 inches. So those are the 5-foot people. And these look like the people that are like 5'1". So they built this really beautiful graph. And they all just lined up, following whatever heights they were. And you can see there's a very few people at the start that are pretty short. And there's very few people at the end that are really tall. And most people are in the middle. That is what a normal distribution looks like. Now, I'm going to somehow change the numbering on this because I'm actually going to do the next page too. Oh, look, it has the same number. So it must meant to be done together. So same thing, part 2. So as I was saying, if you have enough samples of almost any data, you won't, that you measure, you're going to end up with a normal distribution. So whether you're talking about, this one was employees at a cereal factory, and this is how many people have 1 year service. So this one's a cool graph because it shows you 15 people had 1 year of service, and there are 36 people that had 2 years, and 3 years is 56. If you get to 11, there's 200 people that have that, but you're still getting pretty close to that curve. And that curve is kind of like a bell shape, and sometimes they'll just call it a bell curve, or they will call it normal distribution. And in this one, it says the mean is 10.2 years. So the mean looks like it's about maybe around there. And the standard deviation, which we'll get to shortly, is 4.1. Okay, so this is distribution of pizza delivery times, and it says the mean is 30. So normally it takes about 30 minutes to get there, and 30 minutes again is the one that's right down the middle. And so every once in a while you're going to get deliveries that are, whoa, there'll be a very few that are under 15 minutes. Most of them are going to be, you know, like 60, we'll get there, 64%, basically between 25 and 35 minutes. And there's going to be a very few over on this end where you're going to be over 45 minutes. Okay. And as, I guess if I was the pizza company, I will want this to be as small as it could, because maybe if it takes more than 40 minutes, then maybe you're having to give them their pizza for free or for half price or something like that. Don't know. Okay. Carrying on. Every curve is going to be slightly different, but it's all going to have that same general shape with a high point in the middle, which is the mean of the data, and ends that kind of just curve off. So a couple of pictures here, because there's two ideas to get your head around. Okay, so, and I'm sorry, they're a little fuzzy, but it's, oops, best I could do. All right, so in this picture, you can see both of those have, okay, let me back up. This one, this one, this one, and this one. Those are all normal distributions. Okay, it's just a matter of how spread out the data is. So these two in this one have the same mean, and the mean is the middle. But they have different standard deviations. They have different amount that they're spread out. Whereas this one, this graph on this side, see how the shape of them is identical? Okay, so that means the standard deviation is, again, the spread. They're spread out the same amount, but with different means, that means they have different middles. Middles of graphs. So you got to keep those two ideas straight. The mean is where the hump is, and the standard deviation tells you how much it's going to spread out. All right, that's it for this video. Thanks.